now we are ready to develop the second order optimality conditions. In a way, they're similar to what we had in the first order optimality conditions. So again, we will look at the Taylor series approximation around the point of a local minimum. So we'll look at the problem of minimizing f of x, where x is in Rn, an unconstrained minimization problem, and assume that x star is a point of local minimum. And we want to derive the conditions on this point, assuming that it is a local minimizer. So this will be the necessary conditions, right? So in this case, we are shooting for the second order necessary conditions that would involve the second order derivatives. So our f of x, using Taylor's approximation, will be given by f of x star plus the gradient of f in x star transposed multiplied by x minus x star. So this is the linear term. And then we have the quadratic term. So 1/2 x minus x star transposed times the Hessian of f in x star times x minus x star. All right, so then plus the error term will be O small of x minus x star squared. And again, just like we did before, when we developed the first order optimality conditions, we assume that x is obtained from x star by moving in some feasible direction d. So in this case, actually, we are talking about an unconstrained problem. Every direction will be feasible. So we'll just assume that x is obtained from x star by moving some distance alpha in the direction d, where this direction d is assumed to have the norm of 1, right? So alpha here will be the positive step size. All right, so it will be the distance between x and x star. Now, if we replace x with x star plus alpha d in this expression here, we'll obtain f of x star plus alpha d is equal to f of x star plus the gradient of f in x star transposed times x minus x star. And then we need to replace x with x star plus alpha d, right? So what we'll have here will be just alpha d, so we'll put d here, and then the alpha will go here. Then for the quadratic term, instead of x minus x star, in both cases we'll just have the vector alpha times d. And then, because alpha is the scalar, I can move both alphas up front, and they'll give us the product of alpha by alpha, which is alpha squared, right? So we'll have 1/2 alpha squared, and then times d transposed times the Hessian times d. And then for x minus x star, the norm of this squared, we will have the norm of alpha times d squared. The norm of alpha times d is the same as alpha times the norm of d. For the squared one, we'll have alpha squared times the norm of d squared. And remember, the norm of d is equal to 1, so it will be just O small of alpha squared. All right, so and then next we do the same trick as we did before. We will move f of x star to the left-hand side, and then we'll divide everything by alpha squared this time instead of alpha. So we'll have f of x star plus alpha d minus f of x star divided by alpha squared is given by this. We can ignore because, we assume that x star is a local minimum, and if it is a local minimum, then the first order necessary condition must be satisfied, and the gradient of f in x star must be equal to 0. So this term vanishes for us. What remains will be 1/2 alpha squared times this quadratic, but when we divide by alpha square, it will be just 1/2 d transpose times the Hessian of f in x star times d, and then here we have O small of alpha squared divided by alpha squared. Okay, so let's analyze this expression here now. So we assumed that the point x star is a local minimizer, so which means that there is a small neighborhood of the point x star where x star is the best point in that neighborhood, right? So, and then if we select alpha small enough so that x star plus alpha d will be within that epsilon neighborhood for which we have x star as the best point, then this difference here between f of x star plus alpha d and f of x star must be non-negative by local optimality definition. And then, because here I have all alpha squared divided by alpha squared, I can always select alpha that will be small enough for me to make this as close to 0 as I want in absolute value, right? I can always select alpha such that this will be less than any positive number in absolute value, okay? The third term we have here that we need to analyze is this here. So in terms of the sign of this term, we can have it either negative or 0 or positive, right? So now let's assume that it is negative. So if it was negative, then because this term here doesn't depend on alpha in any way, I can always select alpha that will be small enough for us to claim that this expression, this term here, is less than this one in absolute value, right? Therefore, when I add these two together, the sum will also be negative. So if I assume that this is negative, then the whole thing will be negative for small enough alpha. Now, if it was negative here, then I would get the contradiction with the left-hand side, which is non-negative. So I would get the contradiction with local optimality of x, essentially. So this tells me that for this equality to hold, and it must hold for our local minimizer here, I must have this term as non-negative, all right? So we have d transpose times the Hessian of f in x star times d must always be greater than or equal to 0. We could consider arbitrary direction d here, right? So this must hold essentially for every direction d in Rn. By definition, this means that the Hessian of f in x star is a positive semi-definite matrix. So what we have shown here is that if our point x star is a local minimizer, then the Hessian of f in x star must be positive semi-definite. This is what we call the second order necessary condition. If we assume that the matrix of the Hessian is in fact positive definite, not just semi-definite, so we want something stronger than positive semi-definiteness, then if it is positive definite, the smallest eigenvalue is obviously greater than 0, right? Then by Rayleigh inequality, we will have d transposed times the Hessian of f in x star times d will be greater than or equal to lambda minimum multiplied by norm of d squared, right? The norm of d is 1, so this is just lambda min. And then if I use this in this expression here, so then we'll have f of x star plus alpha d minus f of x star divided by alpha squared will be greater than or equal to lambda min plus O small of alpha squared divided by alpha squared, right? And obviously, because lambda min is positive, right? So because the matrix was positive definite, as we assumed, so this will be strictly greater than 0. So this means that for some small positive alphas, f of x star plus alpha d minus f of x star will be strictly greater than 0. And because this direction d is chosen arbitrarily, we can actually conclude that the point x star must in fact be a strict local minimizer for f. And this is our second order sufficient condition here. So let's state second order conditions now. Second order necessary condition first, which we abbreviate as SONC. If x star is a local minimum for the problem of unconstrained minimization, where f is twice continuously differentiable. Then we have the following. So first, usually we include the first order necessary condition as a part of second order necessary condition. So the gradient of f in x star will be equal to 0. And then second, the Hessian of f in x star will be positive semi-definite. So this is SO and C. For the second order sufficient condition, which is SOSC, if x star satisfies the SO and C, second order necessary conditions, you would typically check the second order sufficient condition only for the points that satisfy the second order necessary condition, because if x star is a minimizer, it must satisfy the second order necessary conditions, right? So therefore, first we check the second order necessary conditions to find out if x star is a candidate for a local minimizer, and then if it is, then we check the following conditions, and the Hessian of f in x star is not just positive semi-definite but positive definite, then x star is a strict local minimizer for our problem, the problem of minimizing f of x in Rn. Alright, so this is the second order sufficient condition. So now when we look at the second order sufficient condition, we can immediately see the weaknesses of this condition, so because this condition works only to identify strict local minimizers. If a local minimizer is not strict, you cannot really verify that it is a local minimizer using the sufficient conditions, right?
Well, this is a strange turn of events.
But in many cases, the second order sufficient conditions are helpful. So if we are able to show that they're satisfied, then we have the strict local minimality for our point x star following from this condition.
I think it's working!
By looking at these conditions here, we can come up with a strategy for finding local minimizers, right? So what will be the strategy? Just like we did it with a very simple one-dimensional example, we can try a similar strategy. So what was the strategy with the simple one-dimensional example that we mentioned before? So we took the first order derivative, right? We tried to find all points where the first order derivative is equal to 0. So these are our candidate points for local minimizer. And then what we do, we take the second order derivative and see whether these candidate points are local minimizers or local maximizers by looking at the sign of the second order derivative. And we saw that if the sign of the second order derivative was positive, then we concluded that this is a minimizer. If it would be negative, then we would conclude that this is a maximizer. In higher dimensional cases, we look at this second order necessary and sufficient conditions. So after we find the point x star where the gradient is equal to 0, we are trying to look if the Hessian of f in x star is positive semi-definite. Alright, so if it is not, then the point is not a candidate for a local minimizer anymore, and we reject it. And we focus on the points for which both of these conditions here are satisfied, right? And then we check if the Hessian is actually positive definite, not just positive semi-definite, then we can conclude that x star is a local minimizer. However, if the Hessian is positive semi-definite but is not positive definite, then our second order optimality conditions are inconclusive on whether this point is a local minimizer or not. It can be a local minimizer, it can even be a strict local minimizer, or it can be a saddle point. Our test is inconclusive in this case, so we cannot tell by using these optimality conditions. So we can see that the optimality conditions are of course limited in power, like anything for optimization. So in general, optimization problems are extremely hard. Okay, so when these conditions work, that's great. We can use them to detect if a point is a local minimizer, but whenever the conditions are not applicable, they are essentially useless for some cases. So now with respect to quadratic problems, we can actually use these conditions. They're always useful.
I'll be back.